In this lecture, we're going to see fuzzy clustering and manifold learning. I'm also going to talk a bit about how to compare clusterings with some external indexes and the second assignment. So we're going to start by looking at the idea of fuzzy sets and fuzzy membership to sets and how to use that for clustering. For that, we're going to look at the fuzzy C-means algorithm. And then we're going to look at the problem of reducing the dimensionality of the representation of our data so that we try to preserve as best as possible the structure of the data. We previously saw principal component analysis as one way of dimensionality reduction, but that was just a linear transformation that attempted to preserve as much as possible the dispersion of the data. Now we're going to try to preserve the actual structure, the topology of how our data is distributed. And so we're going to see t-SNE and Isomap as two examples of algorithms for this. So let's start with the idea of fuzzy sets. And in conventional set theory, we have a crisp notion of membership. It's a binary notion. An element belongs to a set or it does not belong to a set, but there is no intermediate case. In fuzzy set theory, we associate the membership of the element to a set with a continuous value between 0 and 1 that indicates how much that element belongs to the set. So more formally, we define a fuzzy set by a set of ordered pairs where we have both the element and how much the element belongs to a particular set. So this quantity between 0 and 1 is what gives us the fuzziness to the fuzzy set, because it means the element may belong only 0.5 or 0.1 or 0.9 and not completely belong to the set or be completely outside the set. There are many possibilities in between. The purpose of this is to model some uncertainty about what we are trying to represent. This can be conceptual uncertainty, some vagueness about the concepts themselves. For example, if we want to classify or cluster temperatures into different groups, and the groups are cold, warm, and hot. There is no clear distinction between cold and warm, for example. So if we have a temperature here represented by this vertical line, we can say that this temperature is mostly cold. There is a large membership to the cold group there, but it's a bit warm. There is a small value of membership to the warm group and not hot at all. So it has a 0 membership to the hot group. So this could be a way to represent that we have a temperature here that is mostly cold, but not as cold as something that is over here, for example. This can also be used to model other types of uncertainty, like uncertainty due to lack of information or to computational limitations or something like that. If we want to assess some kind of risk or credit, the risk that the person we are giving credit to will eventually default on the payments, etc. So this is not a probability, fuzzy membership, even though it's arranged from 0 to 1. We do not interpret it as a probability, but it's a way of modeling imprecision or uncertainty about those aspects that we are covering. So we can create a partition divide the set of data that we have in a partition of C fuzzy clusters if we meet these criteria. So obviously the membership of each example, each element to each cluster K must be between 0 and 1. This is the condition for being a fuzzy set. And also we require that the total membership of any point computed over all the C clusters that we have adds up to 1. This means that the point is completely distributed between the clusters and does not represent more than 1 unit among all the clusters. And also for each cluster, we must require that the sum of the memberships of all the points cannot be larger than the total number of points that we have here. So we cannot have one cluster with more membership than the points that exist. If we respect these conditions, we say we have a fuzzy C partition of X where we divide the set X into C fuzzy sets. And now we can use this to cluster use fuzzy clustering on this set of points. And one example of that is this algorithm fuzzy C-means, which is similar to K-means, but it deals with fuzzy sets. So let's start with a set of data points. We have n data points in this matrix X, and we want the membership matrix, which tells us for each of these n points how much it belongs to each of the C clusters. So this will be a C by n matrix, which has all these membership values there. We also need the centroids of these clusters, these C clusters. So we'll have a set of C vectors with all the centroids for the clusters. And the criteria for computing these centroids and these membership values will be to minimize this squared error function. So this is similar to what we saw with k-means. We are considering the sum over all clusters and all the points of the membership. So in k-means we use that rank function that gives us 0 or 1 depending on whether the point belonged to the cluster or not, multiplied by the square of the distance between the point and the centroid of the cluster. Now here, instead of just using a 0 or 1, we're going to use the membership value of point n to cluster k, and we're going to raise it to a power m, which is the fuzzification factor. So how important the fuzziness of this set will be in determining the result of the fuzzy C-means. So we are going also to subject this to this constraint where we require the sum of the memberships of any point to be 1. So a point is distributed through all the clusters without any leftovers or missing value there. The distribution must add up to 1 when we add all the membership values. And this m value here is typically 2, but this is something that controls how strongly the continuous membership value will influence the result of fuzzy C-means. Okay, so now what we need to do is to minimize this error function. So we're going to compute the derivatives with respect to the parameters that we want to adjust. These are the membership values and the centroids for the clusters. And when we compute the derivatives with respect to these parameters and equal them to 0, which corresponds to the minimum of this loss function, we get this for the membership value. So the membership of a point to a cluster will be 1 over the square distance between the point and the centroid of the cluster, and this in proportion to the sum over all the centroids. So basically we are using 1 over the distance as a weighting factor for determining the membership of a point to a cluster, and then using the fraction of that weight over the sum of the weights to get the actual membership value. Now, during this operation, we also use this m factor here, the fuzziness factor, the fuzzification factor, that influences the nonlinear this nonlinear change here on this factor. So basically we're raising to 2 over m minus 1, and if we increase the size of m, then the fuzziness will become more important relative to what we would have with a crisp membership. So this tells us, given a set of centroids, how much each point belongs to each of the clusters. And then we can also use the derivatives of the loss function with respect to the coordinates of the centroids. And here we can see that this is basically the same thing as we had in k-means, which is the mean of the coordinates of the points in the cluster. But the difference here is that the points are weighted according to their membership and the membership raised to this power m. So this factor here is a weighting factor that gives more weight to some points than others, and the centroid will be placed at the weighted average of all the points that of that cluster. So basically all the points that have a membership greater than 0 for that particular cluster. So with this we can use the same algorithm that or the same general approach that we have in k-means, which is to alternatively use each of these expressions and iterate until we reach convergence. So we start with a random distribution of centroids. We compute the membership values for all the points based on the initial position of the centroids, and then we're going to recompute the position of the centroids based on the membership of the points. And now we're going to repeat this until the change in membership values is sufficiently small for us to consider that we can stop. So because this now is a continuous is a problem with continuous values, we don't necessarily reach that point as we do in k-means, where nothing changes because the membership no longer changes. The membership here can always change by very small amounts, so we can have a threshold value here that if the change is all below some epsilon, we simply stop the algorithm. And the result here is similar to k-means. We have these centroids, but now we don't have just a yes or no membership of each point to a cluster. We have the matrix with the continuous membership values. So this is a fuzzy partition, and we have these membership values to different clusters. So here in one color we have the membership values to this cluster. Here the other color shows the membership values to this other cluster. If we don't want to keep the fuzzy cluster, we want to have a crisp decision assigning each point to a cluster, we can always convert a fuzzy clustering into a crisp clustering by, for example, assigning each point to the cluster with the largest membership value, or computing the nearest centroid will also something similar to k-means, so we just assign the point to the nearest centroid. In any case, it's very easy to go from a fuzzy clustering to a crisp clustering using this criteria. Okay, so now let's move on to a different problem, which is trying to represent data that we have in higher dimensions, represented in a lower dimensional space, but trying to preserve as best as possible the relations between the points. Let's consider this example of this graph here represents the coordinates of seismic events at the surface of the Earth. So these points are spread out in 3 dimensions because the Earth is spherical. But we know that we can easily represent these points in a map because they are all on the surface of the sphere. So this would be a manifold of the original representation, the map, and the manifold is a set of points that respects this condition that the neighborhood of each point is homeomorphic to an Euclidean space. So basically we can transform the neighborhood around each of these seismic events into a lower dimensional space, into 2 dimensions, where we have this homeomorphism, which basically is a continuous inversible function that can map between the 3-dimensional space and the 2-dimensional space of the map. So if we do this, if we represent this in a 2-dimensional surface in this way, we can preserve most of the topology of these points, because they are, although they are in 3 dimensions, they are only covering the surface of the sphere. And so we can find this particular surface and bring it into 2 dimensions. This does not work well for the complete set of points, because when you put this on a map, you will have very strong distortions near the edge of the map, and even when you at one extremity of the map, it will be far away from the points at the other side. But locally, around each point, you can always draw a map that is fairly accurate. So this is the idea of a manifold, and manifold learning is the process of finding the best manifold, or a manifold that is good at preserving the topology of our data. So let's imagine that we have this data set in 3 dimensions. So we have these points going around in this curved line here, and we can see that it should be possible to represent this either in 2 dimensions or in 1 dimension, while preserving this this relation between the points where they seem to be ordered along this line. So this could be something like a protein sequence or a chain or something like that, that has a complex structure in 3 dimensions, but we can look at the sequence of the individual elements as a way to represent this in lower dimensions without losing much information. So one idea would be, for example, to represent this into 2 dimensions while preserving this relation between the points, which ones are close together and which ones are far apart. Or we could represent this in a single dimension. This is just so that we can see the overlap of the points here, but this is not the actual representation. It's this one in 1 dimension, where we are preserving this ordering along the line, even though this has a more complex structure in 3 dimensions. So one example of an algorithm for doing this is t-SNE, T-distributed stochastic neighbor embedding, which basically considers 2 probability distributions. One is the probability of a point I and a point I and point J being neighbors. So we can start by seeing the probability of point I choosing point J as a neighbor, and this we can define by a Gaussian distribution, which is based on the distance between the 2 points. Then we have this sigma here for the variance of the Gaussian distribution, but basically this is a Gaussian curve around point I, and we're going to see use this curve as the propensity for I choosing J as a neighbor, but then normalize this by dividing by the same values for all the points for all the points that are not J. So basically we are looking at how much the Gaussian the value of the Gaussian using the distance between I and J as a fraction of the values of all the other Gaussians for all the different points that are not J. So this can tell us that point I will probably select point J as a neighbor if point J is closer than all the other points. If not, then the probabilities start reducing. We do the same the other way, the probability of J choosing I as a neighbor, and now we just consider that the joint probability of Ji being neighbors is just the average of these 2 probabilities. And this is in the original space. So suppose that we are in 3 dimensions. This will be xi and xj will be vectors in 3 dimensions. Now we also have a lower dimensional representation where each of these x has a corresponding vector, we'll call it y, that has a lower dimension. For instance, 2 dimensions or 1 dimension, something like that. And we also have this same probability of points in this lower dimensional representation selecting each other as neighbors. Now this could be the same thing, the same Gaussian distribution, but since we are going to be adjusting these y values in order to make these 2 distributions fit as well as possible, one optimization in t-SNE is to use this t distribution and not the Gaussian one, because it simplifies the computations here without that exponentiation and so on. So basically we have the same idea here, but now we are considering the probability of I selecting J as a neighbor in this lower dimensional representation as the value of the t distribution given the distance between the two of them as a proportion of the sum of the corresponding values for all points that are not j. So again, if if j is closer to I than other points, then this makes it more probable that they are neighbors. Okay. And now we will do the same thing, average this for the probability of being neighbors. And the way the result is computed, what we are computing here are these representations in lower dimension, is to change that representation so that the divergence between these distributions of probabilities is as small as possible. This is measured by the Kullback-Leibler divergence. Basically, this is the formula for the divergence of these distributions. But the idea is that when we are minimizing this divergence, we are making this distribution of probabilities of points selecting neighbors as close as possible in the lower dimensional space, as close as possible to the original probability of getting neighbors in the original space. So this leads us to a lower dimensional representation that tries to preserve this neighborhood relation between the points, and so preserves the local topology of the data. So this is an example. We start with this original data in 2 dimensions. If we use t-SNE to reduce this to 2 dimensions, we get something like this. t-SNE works stochastically, so this optimization is done with some randomness, and you don't get always exactly the same result. But you can see here that the relations between the points and this ordering here along the line was mostly preserved, although with some gaps in some places, but it was mostly preserved for the set. And the same thing when we project it into 1 dimension. There is some change in the ordering in some segments, but we can see here this kind of ordering along the line. Another example of manifold learning is the Isomap algorithm, and this one is deterministic, and it starts by listing for each point the k nearest neighbors in the original space. So basically we are going to create a graph where each point is connected to its nearest neighbors. And you can imagine this, if we look at this the original data, we can imagine that we are looking at each point and creating connections to those points that are nearby. And so we create a network of connections that follows the close points, the neighbors along this line. And now what we're going to do is to compute the distances between all sets of points, so all pairs of points, we compute the distances, but not going straight across the space, but going along paths in this neighborhood graph that we created. So it's still Euclidean distance in the original space, but only along these neighborhoods. This means that if we are considering, for example, the distance between a point here and a point over there, we are not going to measure this across space, but we are going to measure along the path of the neighbors, so along this line. This means that these 2 points will now become a lot farther apart because we are measuring the distance all along the connections of the graph of nearest neighbors. And this is how Isomap will now preserve this structure. So after we have these pairwise distances going along the path of the neighbor's graph, we compute a low dimensional embedding that respects these distances. Not the distances measured directly in the original space, but the distances measured along the neighborhood graph. And this is an example of what we get when we use Isomap to go from this representation to 2 dimensions. You can see here a good preservation of the structure here along this part, and then a bit worse when we get here to more spread out points. And also it works well in 1 dimension. We have here a strong preservation of this structure. Only at the end here do we get some overlap of the different segments of this part, but it still preserves very well the topology of the data that we have there. So basically the idea of manifold learning is to capture this topology, create this manifold of the data in lower dimensions so that we preserve as best as possible the structure of the data. This is different from what we do with PCA because, first of all, PCA is just a linear transformation, so it has less power than these manifold learning algorithms, and PCA aims to preserve as much as possible of the variance and not the topology. So if we take the same data set and reduce it into 2 dimensions using PCA, we get this result here. So this is just a rotation and a projection of the original data, and we have lots of overlaps here and not a good preservation of that linear structure along this path. And even worse if we convert this into 1 dimension. So we get something that is really weird in 1 dimension. With TSNE and Isomap, we get, or this kind of algorithms, these are just 2 examples, there are others, we have a much better preservation of the structure of the data. There are other ways of doing this nonlinearity reduction and trying to keep the structure of the data. We saw self-organizing maps before. There is PCA using the kernel trick to transform the data, so something similar to what we saw with support vector machines, and this becomes nonlinear. There are autoencoders, which are artificial neural networks where the input and the output are the output tries to be the same as the input, but at the center of the network we have a different representation which can be of lower dimensions. So this allows us to do nonlinear transformations of the data and try to preserve as much information as possible about the structure. In scikit-learn you have several methods for manifold learning. We only saw these 2, TSNE and Isomap, but you have other possibilities there. So if you want, take a look at manifold learning in scikit-learn and you can have an idea of different algorithms for this. So one other thing that we need before the second assignment is how to compare clustering with either other clusters or with some external labels. And for that, we can look at the RAND index. So remember that in supervised learning, we had this idea of the confusion matrix, where we have a comparison between the predicted class and the actual class of the examples. If the example is class 1 and we predict class 1, this is a true positive. If the example is class 1 and we predict class 0, then we have a false negative. Our classifier is saying it's a negative example, but it's false because it's actually a positive example. And so on. So with supervised learning, we can just compare the label of the prediction with the label of the class. But with clustering, we cannot just compare the labels because the labels are arbitrary. Suppose that we have one set of labels on our data that is 0 and 1, and now we have clustering that has labels 0 and 1, but they could easily be switched around. We cannot in clustering force this cluster to be labeled 0 and that other cluster to be labeled 1. It will depend on how the clustering algorithm will end up in. So what we have to do is to compare if for all pairs of points, to compare if they are in the same group and placed in the same cluster, or if they have been incorrectly placed in the clusters. So using the analogous of this confusion matrix for the clustering problems, we can consider that a true positive will be a pair of examples that belong to the same group, so have the same label, same external label, and were placed in the same cluster. We do not require that the label of the cluster be the same as the label of the group that we have, because the labels are arbitrary. But we want that if a pair of points belongs to the same group, then they should be placed in the same cluster. And this is a true positive. A true negative will be a pair of points that come from different groups and they are placed in different clusters. Again, we cannot compare directly the labels of the clusters to the labels of the groups, the classes, or things like that, but we can check if they come from different groups and are placed in different clusters. These groups can be labels such as class labels that we can use for supervised learning, or they can be clusters from a different clustering algorithm if we are comparing different clustering algorithms. So basically, these true positive and true negative are the agreements. When a true positive is when a pair of points that have the same label, the same group, are placed in the same cluster, and a true negative if they come from different groups and are placed in different clusters. And then we have the false results, which is either placing a pair that comes from different groups in the same cluster. This is a false positive. Our clustering algorithm thinks that they are the same, but they are not. They come from different groups. Or a false negative if the 2 points come from the same group, but they were placed in different clusters. And our clustering algorithm is separating points that should be together. So for this case, we need to consider all the pairs of points. So instead of using only n, we have n multiplied by n minus 1 divided by 2. This is the total number of different pairs of points. And we are going to compute all of these, true positive, true negative, false positive, and false negative, for all the pairs. And now we can obtain the equivalent or the analogous in this unsupervised learning framework of precision and recall. So basically we use the same formula. For precision, the true positives divided by all the positives, the true positives and false positives, and recall is the true positives divided by all that should have been positive, the true positives and the false negatives. The RAND index is basically the analogous of accuracy, which is the correct decisions in our clustering algorithm divided by the total number of pairs that we have here. And then we can do the analogous of other measures like F1, for example, using this formula. So using this adaptation, where we are looking at pairs of points and checking to see if they fall in the same group, in the same cluster or different cluster, and compare that with whether or not they were in the same group, we can compute this confusion matrix for clustering that is analogous to the one we had for classification, but without having to actually match the labels of the clusters and the groups or classes, whatever that we have, because the labels are arbitrary and we cannot demand that they be the same. A problem with the RAND index is that it can look artificially high just because we have many cases. If we have many clusters, it's very easy to have cases of points that come from different groups just by chance being assigned to different clusters. So when you have a large number of clusters, even doing the clustering completely at random can give you a high RAND index because you're going to have lots of true negatives in these pairs. One adjustment that we can do this, and it's called adjusted RAND index, is to subtract what would be expected by chance from the RAND index. So this is the adjusted RAND index, where we compute what the RAND index would be if we were to randomly distribute the points in this number of clusters, and we subtract that from the RAND index, and we get this adjusted RAND index that, even though the RAND index is only between 0 and 1, the adjusted RAND index can actually be negative. So we can have something that is performing worse than just dividing everything at random. You can obtain the adjusted RAND index in scikit-learn using this adjusted RAND score. So you can compare the labels of the clusters with the other labels, and you compute the adjusted RAND score by this formula. So this will be used in assignment 2, and assignment 2 will be for clustering. What you have is a set of images. They are all the same size, and they were obtained from fluorescence microscopy. These are images of bacteria of this species, Staphylococcus aureus. and they were obtained by automated segmentation of photographs of the many bacteria. And you can see that in some cases we have segmentation errors here. So this triangular shape here, these fragments like this, these were cases where the algorithm that did the automated segmentation did not manage to identify a complete cell, but only gave us a part. So there are cells here that are complete. They are also in different stages of development. We can see cells here that are at one stage, cells that are starting to divide, and cells that are more along the way to splitting into two daughter cells. So this is the whole set of images that you have. You also have, out of these 563 images, each of them has 50 by 50 pixels, you have also a text file with labels for around 60 images. You don't have labels for all the images, only for a small fraction of the images. So this is not a classification problem because we don't have enough labeled data, but there were some cases where the biologists went to look at the cells and they assigned this small group of cells to one of three phases in the cell cycle. This is phase 1, before the cell starts to divide. This is phase 2, where we can see the initial formation of a septum there where the cell will divide. And this is stage 3, where there is a strong fluorescence there, because we already have a dual layer of membranes there, and the cell is about to split into two. So this is what we have for only a small group of cells, and the labels are here in this file. If the label is 0, this means that the image was not labeled. So this is a list corresponding to all the images that we have here, but many of them were not even looked at by the biologists, so they have no labels. 1, 2, or 3 are the actual labels that they assigned. Now, the objective of this assignment is for you to try to help the biologists using these unsupervised learning techniques that we've been looking at, to try to work something that can help reject segmentation errors, or select cells of the same type, or help the biologists label cells because they can label groups of cells that are similar, something like that. So the idea here is that, unlike assignment 1, where you had mostly to follow the script and implement those things, assignment 2 is more realistic in the sense that you are placed in the role of the data scientist. The biologists don't know anything about clustering and these things, so you must figure out what techniques you can use to do something with the data, to extract some useful knowledge from the data. Part of the assignment, you need to follow the script there in the instructions. So basically, in order to obtain features for clustering these cells, we are going to use PCA, TSNE, and Isomap. This is not the best way of extracting features from images, but extracting features from images is a very specialized problem, and it falls outside the scope of the course. So we're going to take advantage of this as an excuse for you to play a bit with these algorithms. And what we're going to do is to use this to extract 18 features total, so 6 with each of these 3 algorithms, and then you select which features to use. So you don't need to use all 18. It's not a very good idea to try to do clustering in a large number of dimensions because of that curse of dimensionality that we saw previously. So you should select one subset of these that seems to work best for whatever purpose you're trying to apply these algorithms to. And then you must test at least 2 clustering algorithms, k-mean and dbScan. These are the mandatory ones. And for dbScan, you must also use a method that is described on the dbScan paper that I supply, which is a method for finding the epsilon, the radius of the neighborhood that we're going to consider in dbScan. And then you're going to have to implement and measure all of these quality metrics that we saw: the RAND index, the adjusted RAND index, the silhouette score, the precision, recall, and all of those things that we've been seeing. You have a list there in the instructions that you need to compute and show the graphs for those. Now, the rest is for you to decide. You need to then look at all of these metrics and think about which ones are more useful for whatever application you want. You need to evaluate the clustering algorithms, experiment with other clustering algorithms. We're going to see more of them in the future lectures. And basically, you need to think about what is the purpose of this, or what usefulness could have clustering in this particular case, and decide how to use these algorithms and which metrics to rely on. So to do this, I'll put the instructions online, just like for the first assignment. Read them carefully, download the data that you have. You also have this script, auxiliary script, which has functions for generating HTML reports where you can see the clusters that you created with the images there. So basically, this creates an HTML page where you can see the groups of images for all the clusters that you created. This is good for you to do some visual examination of the results and see if the way the cells are clustered together makes sense. So basically, you need to implement just the code necessary to extract the features, train the clusterings and so forth, but you don't need to implement any clustering algorithm here. Just use the ones on scikit-learn. The important thing is to examine the results and answer the questions there. So this assignment will be strongly graded on your answers and your reasoning and what you propose to do with clustering. It's a lot more about thinking about the problem and proposing solutions than the actual code, because the code in this case will not be very complicated. You're just using the clustering methods from the library and doing a bit more like plots and things like that, but nothing complex in the code. As an optional part of the assignment, so this is only worth a small fraction of the grade, you can implement the bisecting k-means and see if with bisecting k-means, with hierarchical clustering, you have a better result than with the other clustering methods. So this one you'll have to implement yourself. We don't have bisecting k-means in scikit-learn, but after you do this, then you can also use the auxiliary functions I provide to represent the hierarchical clusters. You just need to create the data structure specifying that tree for the clusters. But if you follow the instructions there, you can also generate the HTML with the results for this. But this is an optional part because it takes some work and a lot more in proportion to the grade, to how much it's worth on the grade relative to the rest of the assignment. So don't do this before you complete the rest of the assignment. To sum up, we saw fuzzy sets, the notion of fuzzy membership, and how we can apply this to clustering with the fuzzy c-means algorithm. This is similar to k-means, but it gives us a fuzzy clustering in which we have continuous membership values for all the points to all the clusters. We also saw manifold learning, this idea of trying to find a representation in lower dimensions that preserves as much as possible the topological relations between the points in the original representation. And then we saw a bit about how to compare the clustering with some other labels. These can be labels given by in the data or given by other clustering algorithms, something like that. And this is something that you're going to need for the second assignment. So if you want to, you can read this page on that scikit-learn has on manifold learning. You have there lots of examples for other manifold learning algorithms other than the two that we saw here, and you can play around with them and easily see the results there.